Okay, well, thank you very much. So it's a bit of a math interlude. So I'd like to tell you about these pictures. So a spectrahedron, by definition, is defined by a linear matrix inequality. So a spectrahedron of degree n in R to the d is given by d plus 1 n by n real symmetric matrices, A0, A1 up to AD. We take the affine linear combination and require that this matrix is positive semi-definite. So what do these objects look like? Well, for example, if n is 1, we have 1 by 1 symmetric matrices. Then a spectrahedra is simply a closed half space. When n is 2, we take 2 by 2 symmetric matrices. We get a quadratic cone. So for example, in 3 space, they look like this. Another very basic observation is the intersection of an finite intersection of spectrahedra is again a spectrahedron, right? Because you can stack up the matrices along the diagonal and take a bunch of small symmetric matrices and make bigger symmetric matrices. So finite intersection of spectrahedra is a spectrahedra. So taking the first statement and the third statement, we learn that every convex polyhedron is a spectrahedron. A convex polyhedron, by definition, is an intersection, finite intersection of closed half spaces. Now, convex polyhedra are, of course, very, very useful because they are the feasible regions in linear programming. Spectrahedra are the feasible regions in semi-definite programming. Convex polyhedra, the mathematics, geometry, and combinatorics of convex polyhedra has been studied for 2,000 years, while the combinatorics and geometry of spectrahedra is a relatively unexplored topic to be discussed in this lecture. So most of my examples today, most of my pictures will be for d equals 3. So most of my spectrahedra will be in 3-dimensional space. But I'm going to start out with d equals 2, just to kind of get a sense how these things look like. Okay? So semi-definite optimization or semi-definite programming, as I said, is the computational problem of minimizing a linear function over a spectrahedron, which is the non-abelian version of linear programming. Right? Linear programming concerns diagonal matrices. So linear programming is semi-definite programming for diagonal matrices, but here we're doing general symmetric matrices. So for example, if n is 3, then we look at the 6-dimensional cone, convex cone of positive semi-definite 3 by 3 matrices. That's a 6-dimensional cone. We cut it with a 2-dimensional plane, namely the screen plane, and we get this red convex body. So this is a 2-dimensional spectrahedron of degree 3. Now what can we say about the algebra and the geometry of this? Well, there's a polynomial that vanishes on the boundary, that vanishes on the red boundary. Well, that's a polynomial of degree 3 called the symmetric 3 by 3 determinant restricted to the screen plane. So this is a plane cubic curve. And it's smooth. This is an elliptic curve. Now you might not, on the face of it, see the black stuff, but that's part of the real curve. So if you take that cubic polynomial in the 2 variables of the screen plane, and you ask Mathematica or Sage to plot that curve, it will plot both the red part and the black part. As a warm-up, let's solve a semi-definite program over this spectrahedron. For example, go northeast. Okay. Well, let's record. We don't know how to do this. Let's just do this using calculus. So we're going to record the critical points. So whenever there's a critical point, so we're going to go northeast. I'm going to say beep whenever there's a critical point. What? Beep, 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 beep. I said beep 6 times. 2 red beeps. 2 black beeps, 2 complex imaginary beeps you didn't hear. At the bottom, we have the dual picture. Duality is very, very important in convex optimization. It's equally important in projective algebraic geometry. So here's the dual picture. So we pop open the second window, and the points in the second window correspond to the lines in the first window. And the lines down here correspond to the points up there. So the sweeping through corresponds to stabbing this dual curve with the line. So this dual curve here, the red one, that's the dual convex body to our spectrahedron. And then the black stuff is the rest of the dual curve. So the points on the dual curve are lines that are tangent somewhere at the primal curve. So for example, as I travel the point down here, I have a line, travel a line that's tangent somewhere. The sharp corners correspond to the three special lines that are asymptote that you see in the primal upstairs picture. So in classical geometry language here, we have a curve of degree 3 and class 6. Down here, we have a curve of degree 6 and class 3. Please interrupt me at any time with questions. You know, the previous speaker went way too fast and ended, half an hour earlier, so I can go half an hour over time. No, I won't. But if you have any questions, please interrupt me. Okay? So this is a spectrahedron for n equals 3 and d equals 2. Let's up the dimension by 1. Now let's take our 6-dimensional ice cream cone, our 6-dimensional cone of positive semi-definite matrices, and now slice it with a 3-dimensional plane. And then we get this familiar golden picture. This is sometimes called the elliptope or the somoza. Statistics, this is the set of all 3x3 correlation matrices. 3x3 positive semi-definite matrices of this form. So I'm plotting in 3 space all points with coordinate x, y, and z that make this matrix positive semi-definite. And this is the golden picture. And you've probably seen pictures, versions of these pictures somewhere. Now this somoza, this elliptope, has 4 special vertices, sharp corners out here. They are the rank 1 matrices. So a general point in this space is a rank 3 matrix. If I'm on that surface, if I'm on that cubic surface given by the vanishing of this 3x3 determinant, then I'm at a rank 1 matrix. But we're really interested in low rank solutions, so we're going to be really interested in the 4 sharp corners, the vertices. They are the rank 1 matrices. So in this 3-dimensional space, sir?
The surface is rank 2 or rank 1?
On the surface, it's rank 2.
Okay.
So this for general x, y, z, the matrix has full rank 3. And then this bichromatic surface is the set of all real points where the rank drops to 2. And then there are 4 special points where it drops further to 1. Okay. Now I'm also drawing the other real stuff, the elephant ears. There's a risky closure. So these are all the points x, y, and z where this determinant also vanishes, but where there's 1 positive eigenvalue and 1 negative eigenvalue. So the golden points have 2 positive eigenvalues and 1 negative eigenvalue. The red points have a positive eigenvalue, a negative eigenvalue, and a 0 eigenvalue.
You said negative, I think when you meant 0.
What did I say?
The
golden is plus 0.
Plus 0, yes.
Yes, here what did I say? Plus minus 0. Okay, thanks, nothing. Okay? So that's the picture. Now, here's a question. Does every cubic spectrahedron have these 4 nodes? It looks like whenever you see these pictures, they're always, these 4 corners. And the answer is no, right? That was the title page, right? So it turns out, just like in the study of polyhedra, that goes back to 2,000 years, to people like, Euclid and so on, right? You can study the combinatorial type of spectrahedra, for example, according to the number of nodes they have. So here we see there are 2 possibilities, right? So either we have 4 nodes, we have the somoza, or we have this little lemon drop that has 2 nodes. And the edge between the 2 nodes is actually contained in the boundary of the spectrahedron. Okay. So either 4 nodes or 2 nodes. And one question I like to start to discuss in this lecture, what about larger degree? For example, what about if we don't take a 3 by 3 matrix? What happens if we take a 4 by 4 matrix? Now this is a very relevant observation here. So in particular, whenever you have a three-dimensional spectrahedron of degree 3, there's always at least one singular point. There's always a rank 1 solution. Okay, so that exists with positive, strictly positive probability. If you solve your SDP on this golden spectrahedron, you'll hit a rank 1 matrix, which is a desirable thing. A couple words about sum of squares. Of course, many of you are familiar, but you just sort of summarize it. In global optimization, suppose we're given a polynomial f in m real variables, x1 up to xn of even degree 2d. Suppose we knew that this is bounded below and attains its global minimum, x star. We want to compute it, right? So that's equivalent to finding the largest lower bound, maximum lambda, such that f minus lambda is non-negative, and that's a hard problem in any sense of hard. We can look at the relaxation, where we maximize lambda such that f minus lambda is a sum of squares of polynomials, and that problem is much easier because it's a semi-definite program. Empirically, it often happens that the optimal value of the SDP agrees with the global minimum. So it is not the case in general that these two problems are equivalent, because not every non-negative polynomial is a sum of squares. But it seems to be the case that frequently when we run this, we will be at the optimal point. At that optimal point, we're often lucky. The dual solution often will be a rank 1 matrix. A rank 1 matrix looks like this. It's a product of a column vector and a row vector. They are the same vectors. And then looking at that vector, we find the optimal solution x star. Suppose my beeping 10 minutes ago didn't make any sense because you never took calculus, or you forgot everything that you learned in calculus. So let's solve a calculus problem without calculus. Let's find the global minimum of a polynomial in one variable of degree 4. 3x to the 4th plus 4x cubed minus 12x squared. So that's an instance where m is 1 and d is 2. Okay, so we don't know calculus, right? So we'll do it using sum of squares. So we're looking at f minus lambda. We want to find the largest lambda so that this is a sum of squares. That is to say, it's a quadric in quadrics. It's a definite quadrics in quadrics. So make my ansatz. I write down a 3 by 3 symmetric matrix with the two parameters. There's the lambda, and then there's one free parameter mu. I multiply with the row and column vector of all monomials up to at half the degree. That's a valid identity. And our problem is to find the pair lambda mu such that the matrix is positive semi-definite and lambda is maximal. We take this instance, we type it into MATLAB, and in 0.000001 seconds the answer will come back. But first, this is exactly this picture. Right? Because now we are in the lambda mu plane. We're optimizing the lambda direction. So this is exactly, a 3 by 3 spectrahedron in 2 dimensions, mu and lambda. So we're doing exactly an optimization problem over the red part of my elliptic curve. Question?
Sorry, I'm not sure I understood. How did you get mu into the picture? It wasn't part of the problem.
So yes, so I wrote down the general. So this is, so I've given f. And f is a quartic polynomial. And so as a quartic, I can write it as a quadric in quadrics, non-uniquely.
Right.
But this mu exactly captures that non-uniqueness.
So is that all the non-uniqueness?
That's all the non-uniqueness. So I'm sorry, it's a quadratic in quadrics. So it's a quadratic in quadratics. Right? So if you give me any polynomial here of degree 4 in one variable, so I have 5 free coefficients, And then you sort of count parameters. There's 6 entries in the 3×3 symmetric matrix. So there's 1 degree of freedom. And I sneak in the mu to get that. Excellent question. Other questions? OK, so let's solve it, right? So the optimal solution is -32 minus 2. You plug back in, right? So now we're at the boundary. We're at a rank 1, a red rank 1 matrix. So I take this 3×3 matrix, I Cholesky factor it into a 3×2 matrix times its transpose. I can rewrite this as a sum of squares. And so you see F is the sum of 2 squares plus the optimal value. So we have a proof, a certificate that -2 is the global minimum. And this, as you know, as many people in this audience know, that this works very well for many polynomial optimization problems. OK, so the talk begins now. So in this talk, which will last 45 minutes, I like to do 2 things. Objective 1 is to show many pictures. So I'm an algebraist. Algebraists, by definition, are the people who show pictures. So that's objective 1. Objective 2, I like to tell you about 2 recent papers that I was part of. One is called Quartic Spectrahedra, and there are 3 co-authors, including Cynthia, who is here. And then there's a second paper called Generic Spectrahedral Shadows. So I'll take about 20 minutes per paper. On the pictures, here's again the Somoza. So that's n equals 3, d equals 3. Here's the same picture, just to highlight the nodes. The surface comes out of the nodes. Here's the dual convex body. It's always good to draw the dual, right? So if you have that red convex body, the red spectrahedron, what you do is you take 4 quarters, coins that are circular, and you make them touch pairwise. Well, there's still some holes, right? And you fill in the holes with this surface. That's the Quartic Steiner surface, and that makes the dual to this convex body. Well, these are the 4 planes. These are the planes spanned by the 4 quarters. So this picture tells you what's happening, right? So if James gives me a random linear functional that I want to optimize, well, James' instance either will be a linear functional that's here in the round part, or it will be a linear functional that's in the quarter, in the circle. If James gives me one that's in the circle, that means that his linear function is optimized at a vertex, a rank 1 solution. But if he gives me a linear functional that's out here, it will be optimized at a rank 2 solution. Okay? So that's the dual convex body. Now Ben Recht, in his first talk, actually reduced one of his problems to semi-definite. Is Ben here? So semi-definite. Hi Ben. So in your talk, you reduced one of your problems to a 4×4 semi-definite program. So that's what I'm going to talk about. Quartic Spectrahedra. Let's see some examples. So here's an example of a quartic spectrahedron in 3 space. So I'm going to write down this triplets matrix with 1s on the diagonal. And then that's defines a 3-dimensional spectrahedron that looks like this. Okay? This is quite a special spectrahedron. This is the convex hull of the cosine curve. So you look at cosine theta, cosine 2 theta, cosine 3 theta. That's of course an algebraic curve. And theta either runs over all real numbers, but it's enough to go between 0 and pi. So the curve sort of goes back and forth. It travels for a while, and it goes back. Right? So as the parameter, it goes back, and we take the convex hull. In the boundary of that convex hull, we have 2 quadratic surfaces, a red surface and a turquoise surface. And these are simply the cones over these 2 special singular points. You take the cone over the curve. You have a cubic curve. And you take the cone from the 2 endpoints. These are quadratic surfaces. And so algebraically, this means that this determinant, the determinant of this matrix, factors into two quadratic factors, so you can make a change of basis that replaces this by two 2x2 blocks. This example. Here's the dual picture. Here's the dual convex body. And here you see already an interesting feature. In the dual convex body, you have an edge of this dual convex body that is not an exposed edge. So, and remind you that for convex bodies, there are two notions of face. Okay? A face is a subset with the property that if two points are in the face, it's a subset with the following property. If a point lies in and that point is on the segment between two other points, then these two other points are also in the subset. Okay, you have to unravel that. That's the definition of face. There's also a definition of exposed face. An exposed face of a convex body is a subset at which a linear functional attains its minimum. Every exposed face is a face, but not every face is exposed. So here this edge is a face, but it's not exposed. There's no linear functional that is minimized exactly at that edge. It is a feature of spectrahedra that every face is exposed. In a spectrahedron, every face is an exposed face. So therefore, spectrahedra, the class of spectrahedra, is not closed under duality, right? Because here I have a spectrahedron, every face is exposed. Here I have the dual of a spectrahedron, it has a face that's not exposed. Here's another spectrahedron, the pillow. So it's very similar, just changing the off-diagonal entry somewhat. The spectrahedron looks like a kind of pillow that many of us sleep on at night. Now it has four straight edges.
So, Bernd, can we come back to the previous comment? But the cone of all PSD matrices is self-dual. So how does this duality break? It's because of the...
Yeah, because here, these objects, so let me repeat what Nati said. So the cone of positive semi-definite matrices, the full 6, or in this case 10-dimensional cone, is a self-dual cone in 10-dimensional space. But if I take that 10-dimensional cone and I slice it with the 3-dimensional plane, I get this picture. This picture I get by projecting. So the operations of projection and intersection are dual operations, and they do different things. So we're not, the family of spectrahedra, unlike polyhedra, is not closed under duality and projection. When you hear this for the first time, that sounds like a flaw, right? Because we're all so familiar that if we have polyhedra, we cut them, we project them, we dualize them, we get again polyhedra. That is false for spectrahedra, but that is a feature. That is a good thing. Does that answer your question?
So a projection of a spectrahedron
is not in general a spectrahedron.
So what's the closure? If you take this family and you want to close it?
Yes, so we call these objects spectrahedral shadows. So well, we'll get to it. So a spectrahedral shadow is what you get by iterating this construction. Okay, so here is a quartic spectrahedron. So this matrix actually, if you take the determinant, does not factor, right? So it looks like, when you draw the picture, it looks like that there are two parts of the boundary. There's the upper red stuff of the pillow and the lower green stuff of the pillow, but they are both parts of the same irreducible quartic curve, the pillow boundary. Okay, just to make sure the audience is on the same page, I'm going to pick on a volunteer. Rishi, what do you think? Is the convex dual of a spectrahedron again a spectrahedron?
Not necessarily.
Not necessarily, right? So, exactly. So this is the picture. This is actually not a spectrahedron. So now, the dual to the pillow, again, you would take it by taking 4 quarters, one for each pillow vertex. But now you take the 4 quarters and you arrange them, It's a bit hard to see. There's a quarter, a quarter, a quarter. You arrange them in a circle, and then you glue in this dual surface of degree 12.
But I guess the dual is always a shadow.
The dual is always a shadow, exactly, by the same argument. The dual you can always get by projecting the PSD cone or appropriate slice of the PSD cone, absolutely. Now, we're going to use some algebraic geometry to study these objects. And whenever we apply an applied algebraic geometry, we take a difficult problem that involves real numbers and inequalities, and we make it easier in 3 steps. Step 1, ignore all inequalities. Step 2, replace the real numbers by the complex numbers. That makes the problem much easier. Step 3, replace affine space by projective space. You're done with that. That means any 2 circles in the plane meet in 4 points. Okay? When we're done with all of that, when we're down in complex projective space, the problem has become so easy that maybe even algebraic geometers can say something about it. So we're going to work in complex projective space P3 with 4 homogeneous coordinates x, y, z, and w. By a symmetroid, I will mean a surface of degree n whose defining equation is the determinant of a 4x4 symmetric matrix whose entries are linear forms in x, y, z, and w. It's a little proposition. If the coefficient matrices A, B, C, and D, so these are real n by n symmetric matrices, if they are generic, random, dense open set, then the singular locus of this surface consists of n plus 1 choose 3 nodes. These are the simplest singularities. These are the little corners that we saw on the samosa. So for example, if n is 2, the blue number is 1. Right? Those were my quadratic cones at the beginning. If n is 3, this number is 4. Right? So a cubic spectrahedron is expected to have 4 nodes. If n is 4, this number is 10. Now then, this family, this is a 3-dimensional space of symmetroids, of symmetric matrices, contains no matrices of rank n minus 3 or less. And then the matrices of rank n minus 2 are exactly those nodes. So if these genericity conditions hold, I'm going to say S is a transversal symmetroid. So transversal because I have my cone of positive semi-definite matrices, say, and this is a plane I'm cutting with a 3-dimensional plane that is transverse. These are the conditions for transversality. I'm going to use the same language. I'm going to say a 3-dimensional spectrahedron is transversal if its algebraic boundary, the surface that makes up the colorful boundary, is a transversal symmetroid. Again, for simplicity, if you see some colorful surface in 3 space, such as the cylinder back there, to make it simpler, we think about the corresponding complex projective surface. That's an object that's much easier. So the problem, therefore, is to study the geometry and combinatorics of the general case. So in this talk, I like to talk about the general case, transversal spectrahedra. So for example, how many of the n plus 1 choose 3 nodes can lie on the boundary? That problem is interesting for applications because these are the low-rank solutions. Peter.
Fine. What is a transversal spectrahedron?
So I'm going to say a spectrahedron is transversal if the corresponding symmetroid, the corresponding boundary surface, satisfies these genericity conditions. Okay. So we know for cubic spectrahedra, that's the either the samosa with 4 nodes or the gumdrop with 2 nodes. Okay, so what about the next case?
So the one with 2 nodes, is it also transversal or is just?
Yes, they're both transversal. Okay, so here we're taking the 6-dimensional cone of positive semi-definite 3x3 matrices. And there are 2 types of random 3-planes. There's some random 3-plane that makes this one with positive probability, maybe 57%. And then with complementary probability, maybe 43%, we get that one. And everything else happens on a measure 0 set. Okay? Those are two types.
So does it even make sense to quantify these probabilities?
Sure. So if you have somebody who can actually do integrals like Peter, then we can actually evaluate these integrals.
So there are two other nodes that we don't see or so?
There are two other nodes that are complex, exactly. So there are always four complex nodes that we don't see. Maybe I should make a remark. So how would an algebraic geometer draw this picture? Let me sort of draw the picture for algebraic geometers. So this is a cubic surface. A general cubic surface is a beautiful object that has 27 lines on it. And the way an algebraic geometer would construct it, you would blow up 6 points in the plane. So you would take the plane and you apply a transformation that's called blow up at 6 points. Now these spectrahedra are obtained by 6 special points that are gotten by intersecting 4 lines. So if you take 4 general lines in the plane, they make 6 points. Right? Now under this blow up, the lines become, the 4 lines, they get mapped to the 4 vertices on this surface, and the 6 points get blown up to the 6 edges, the 6 lines on the spectrahedron. Okay? Now this is defined over the real numbers, right? So this is a configuration, a highly reducible curve of degree 4 over the real numbers. And over the complex numbers, there's only one possibility, right? Over the complex numbers, any 4 lines in general position are equivalent under projective transformation to any other 4 lines. But over the real numbers, there are actually 3 types. Either you can have 4 real lines. So you have a configuration like this where each of the 4 lines is defined over the real numbers. That makes this picture. Or you could have 2 real lines and 1 complex conjugate pair of lines. Right? So 2 of the lines are given by a that is a real configuration. Right? If you take it all together, it's defined over the reals. That gives this picture. Or you could have 4 lines that are 2 complex conjugate pairs. And that makes the empty spectrahedron. Okay. So let's see what happens for 4x4 matrices.
One question.
Yes.
You said this everything else happens on a set of measure 0.
Yes.
On the set of measure 0, could you have a different number of nodes?
You could have, yes. You could have up to 16.
Okay.
Yes, you can have 16 nodes. That's the Como surface. Okay, let's. So I was very interested in this question for Quartic. So I went around 5 years ago asking people, and we did some experiments. So we've generated random instances. So we've generated, 100,000 4x4 matrices, and we counted the number of nodes, and it was always at most 8. Okay, there were 10. It's easy to make 10, but they were not on the golden spectrahedron. So I asked this question, and then. Turns out that an answer was given by 2 real algebraic geometers, Degtyarev and Itenberg, and they answered my question with the following remarkable theorem. So there exists a transversal quartic spectrahedron with beta nodes in the boundary and sigma real nodes all together. So the complex surface has 10 nodes, and of those 10, sigma are real, and of those, beta are in the boundary of the spectrahedron, if and only if the following condition is satisfied. So there's some trivial conditions and some non-trivial ones. So, well, certainly these numbers are non-negative because they count things, and certainly sigma is bigger than beta. Okay? Now sigma is even. That's because if you have 10 solutions and then you travel through space, it'd be 8, 6. So the number of real solutions jumps by 2. The non-trivial fact is that beta, the number of nodes on the spectrahedron, is also even, and sigma is at least 2. So on the surface, on the multichromatic surface, there will be at least 1 real node whenever you have a non-empty spectrahedron. Okay? Now this was amazing. So they sent me the paper, and I was really, really happy. They answered my question, and it was a 35-page paper, and I didn't understand a word of the proof. Okay? So it turns out that the proof is very, very indirect. It rests on something called the global Tirelli theorem for K3 surfaces, which I will spare you the details of. and deep topological results for the moduli space of real K3 surfaces. So these guys had studied this kind of stuff all their life, and they applied everything they knew and solved my problem. Okay. Now, I asked them, can you actually find matrices? Is it possible to actually construct, so there are 20 conditions. So if you look at this, there are 20 possible cases. Right? So if you look over all integers beta and sigma that satisfy these things, there are 20 combinatorial types, and the question is, can you actually build spectrahedra? And these are very, very non-constructive techniques, so the answer was no. So in this project that I'm reporting about with Cynthia and 2 Norwegians, we give a new direct proof, and in particular, we give a construction. So let me show you the if direction. So the proof of the if direction is a list. Okay, so here's the proof of the if direction, right? So these are the different combinatorial types. So this is always beta sigma. So for example, sigma beta. So for example, 4, 2 means that there are 4 nodes on the symmetroid, on the real symmetroid, 2 of which are on the spectrahedron. And this is representatives, matrices A, B, C. Okay, so there's a list. You can take these matrices, type them into Sedumi, and see what happens. Okay. We say a few words, so here's back to pictures.
I have a question.
Yes, Luke.
Did you expect all of the examples to have integer entries in the matrices?
You can make it, yeah, because we're in a dense open set. So these are the generic cases. So I'm in the space of 4 tuples of symmetric 3 by 3 matrices. That's a 40-dimensional real space. And then in this 40-dimensional real space, there's an open set that makes a non-empty spectrahedron. And this open set is cut up into 20 open sets. I'm going to pick an integer point with small coordinates in each open set. So making these coordinates small wasn't so easy. Okay, but we have a list. Okay, so here's a picture gallery. So for example, here's a spectrahedron of type 2,2. Okay, so this egg is a spectrahedron, has 2 nodes, and both of these nodes are on the spectrahedron. So the dark blue is the spectrahedron, and the light blue is the rest of the symmetroid. Over here you have an 810 specimen, so they're all 10 nodes are real. 8 of them are on the spectrahedron, 2 of them are off the spectrahedron. Here's a nice one. Here's a 010. Okay? So there are 10 real nodes on the surface, but 0 are on the spectrahedron. And this is a projection of this. Okay? Let me talk a little bit about projecting these things into the plane, because we're going to get to projections in a moment. But before we do that, let me state the main theorem. So the if direction is proved by making a list, and the only if direction is proved using a theorem that goes back to Arthur Cayley. So this is a theorem, the first half of which was proved by Cayley in 1869, and the second half was in our paper. So here's the theorem. Suppose we have an irreducible quartic surface S in 3-dimensional space. Okay, so given by a polynomial of degree 4. And P is a singular point that's a node. So we're going to place a camera on that node, and we're going to take a picture. We're going to project from that node into the plane. Okay? Then the following 2 conditions are equivalent. So this is Cayley's theorem. Condition 1, S is a symmetroid. Symmetroid on P corresponds to a rank 2 matrix. Okay? So that means the surface has a representation by a symmetric matrix of linear forms, and the special point P is a rank 2 matrix in that 4x4 matrix. Condition 2 is the projection from that node into the plane has a branch locus that consists of 2 cubic curves, C1 and C2, that are totally tangent, I'll explain that are totally tangent to a common conic. Here's the picture. Okay, so here you can see in green there's a cubic curve, in red there's another cubic curve, and then in dark blue you have the projection of the spectrahedron, And then in light blue, you have the projection of the rest of the surface. So here's the symmetroid with the spectrahedron. And it looks like this. And then in addition, there is a circle. There's a conic, which is basically the neighborhood of the camera. Right? So the camera sits on the surface, and it sees a little circle. That's the circle. Okay.
What's the node that you project on?
This is a node that's off the spectrum. In this example, I took a node. So this was a 6-4 type. There are 4 black nodes on the spectrahedron. There are 2 nodes outside the spectrahedron, maybe where Kaya sits. And then she takes a picture, and that's the picture. And then the circle, is the circle around her camera, and it's totally tangent. Totally tangent means that the cubic curve meets the conic in 3 double points. So in general, if a cubic meets a conic in the plane, they will meet in 6 points, but here they meet in 3 double points. So this was known to Cayley. The little new addition is what happens over the real numbers. So over the real numbers, the pair P comma S is a real pair, meaning the surface is defined over the real numbers and the point has real coordinates, if and only if the reducible curve of degree 6, C1 union C2, together with the conic is a real pair. And there are 2 cases. Either the 2 cubic curves C1 and C2 are both real, as in this picture, then P is not on the spectrahedron. It's maybe in Kaya's position. Comes to possibility 2, P is on the spectrahedron. In this case, the 2 cubic curves are complex conjugate pair. Okay? So this characterizes geometrically what happens as you project the symmetroid together with the spectrahedron into the plane, and this is used to prove the only if direction. Use the same picture again, so quartic spectrahedron, a projection from the outside node, and you can see the characteristic feature is that the projection ramifies along 2 cubic curves, each of which is totally tangent to the circle. That's the view from the camera. Okay, let me wrap up this part of the discussion by looking at an example with beta equals 0 and sigma equals 10. So let's take this 4x4 symmetric matrix, and maybe we dehomogenize by replacing W by 1 minus X minus Y minus Z. Okay. And that's the picture. Now the question for the audience is, what will semi-definite programming do for this instance? So Jim takes this matrix and gives it to an OR student at Cornell, and that OR student picks random linear functionals 10,000 times and looks at the optimal matrix and say, do me, what's the rank of that optimal 4x4 matrix? Question clear? Yeah. So I take this matrix, I replace W by 1 minus X minus Y minus Z. I pick a random linear function on X, Y, and Z, and I minimize subject to this being positive semi-definite, and I get an optimal 4x4 matrix of rank 2. Right? Because there is no rank 1 point on this dark blue spectrahedron.
Rank 3.
I'm sorry, rank 3. This is a 4x4 matrix. I get a rank 3. Every point, every blue point has rank 3. The only rank 2 points are the black points, but they're away from the spectrahedron. So this example shows that unlike in the cubic case, we cannot. There are instances where the rank may not drop by 2. All the optimal solutions are smooth points. Okay, so this was the second part of the talk. So I talked about quartic spectrahedron. So this was intended as a beginning of an exploration of the combinatorial types of spectrahedra.
So you mentioned that this theorem was proved using all this heavy machinery, but did you explain how you came up with these constructions, and whether you have now an alternative proof, or that's the only proof?
Yes, so there are 2 proofs. So there's the theorem. So this is the theorem. And there are two proofs. And this is very, very, very heavy machinery. And this is much easier 19th century machinery. So we have a new proof that's based on the projections into the plane.
So this parity condition on beta and sigma comes out of this Cayley theorem?
That is correct. So that comes out of the proof. So if you analyze very carefully what happens here, then you get the parity condition and you get the lower bound on sigma.
This gives you a systematic way of constructing.
And it gives you also, well, yes. So this also you draw. I mean, it sounds easy, but it's a little tricky, right? So all you need to do is, to draw circles in the plane and cubic curves that are green and red that touch like this. And you have a certain amount of control doing that, and then you go back. So basically you control this three-dimensional body by controlling this two-dimensional picture. Cynthia is smiling because it wasn't quite so easy, but it's certainly easier than the other proof. Okay, new topic. So Kangjin, you can reboot. New topic, forget everything I said in the last 20 minutes. I'd like to talk about what some people call extended formulations or lifts of semi-definite program. So we define a spectrahedral shadow to be a projection of a spectrahedron, or algebraically, a spectrahedral shadow is a subset of d-dimensional space, vectors x1 up to xt, such that there exists some other vector, y1 up to yp, such that a linear combination of matrices ai, d of them, and bj, p of them, plus a constant c is positive semi-definite. So I'm specifying a spectrahedron upstairs in d plus p dimensional space, and then I eliminate the y variables. I project into the space with the x coordinates. Now, of course, if there are no y variables, that's exactly spectrahedra, right? So if there's no existential quantifier, these are exactly the spectrahedra that we discussed. And these are intersections of the cone of positive semi-definite matrices with an affine linear space. So spectrahedral shadows are projections of spectrahedra. Now there's sort of one big conjecture in convex algebraic geometry, namely that every closed convex semi-algebraic subset of D space is a spectrahedral shadow. So every convex optimization problem in this family has a extended LMI representation. But the bad news is that even if this is true, is the dimension of the lift that you have to go to is very, very high dimension.
Is there any way to explain just briefly the motivation for the conjecture? Why you expect it to be true?
I'm not sure I expect it to be true. It's been proven in many cases. So there is a systematic way of constructing, so using the Lasserre SOS construction, you can get approximations. And then if you're lucky, many of these approximations in the limit will be exact. And that's one way. So one way to construct these lifts is to run some kind of a hierarchy. Question?
But given that we know simple examples where these hierarchies don't converge in a finite number of steps, then, why is the conjecture reasonable in that case?
I don't think it's reasonable.
Well, it's proved in dimension 2.
It's proved in the non-singular case.
It's proved in many cases.
In the non-singular case.
So many people, such as Daniel and Pablo, and many people think that this is a very interesting and important conjecture, and it's been proven in many cases. I'm not saying that I find it interesting, but many people find it interesting. So I'm going to be interested in generic case. So I'm going to do something that we always do in algebraic geometry. I'm going to look at the data that are generic. So let me assume AI, BJ, C are random, symmetric, 3x3 n by n matrices. So there's some crazy discriminant in the 40-dimensional space of matrix tuples. I'm going to pick an instance outside that space. Okay? Now that's a very unreasonable thing to do in this audience, because all SDPs and SOS instances you will ever see will be very, very special. Okay? So every particular SDP problem that's ever been studied at the University of Waterloo will lie on that discriminantal hypersurface. But I'm going to analyze the random case first, the generic case. Okay, so I just said there are 20 types. For example, if n is 4, d is 3, and p is 0. So the first thing we might ask, let me take one of these blue things and project it into the plane. So what do you get by projecting from R3 into R2? Okay. So what is the degree and number of singularities for the boundary curve of a generic spectrahedral shadow? And again, the parameters, n is the size of the matrix. So these are 4 by 4 matrices. D is the image dimension. That's the number of x variables. And p is the number of y variables that I eliminate. That's the codimension of the projection. Say this again. We have upstairs a p plus d dimensional space. We write down an n by n matrix. We eliminate p variables, and we're projecting into a d-dimensional space. I want to ask the question, what happens? So this is a question that I find more interesting. Namely, suppose I have a convex, semi-algebraic, closed, basic, whatever set in the plane. We know by a theorem of Scheidor it has a lift. By a Lasserre construction, it can be lifted into some dimension. But I'm interested in, can it be lifted into dimension 3? Okay. Given a curve in the plane, does it come from 3 space? Well, the obstructions are quite serious. Let me hint at that. So here's what happens if n is 4, d is 2, and p is 1. Well, the algebraic boundary of the spectrahedral shadow will be a curve of degree 12. Well, because I have a quartic surface. The ramification locus is given by taking a derivative. So the derivative of a polynomial of degree 4 has degree 3. 4 times 3 is 12. So by Bezout's theorem, the ramification curve is a curve of degree 12. This degree 12 curve is very, very, very singular. It has 46 singular points. 10 of these singular points are the images of the nodes. So here's a specimen where we have 10 blue nodes on the spectrahedron, and their images in the plane are singular points on the curve. So for example, this singular point is a singular point of the complex curve that's isolated in the real plane. It's clear, it's like x squared plus y squared equals 0, right? So x squared plus y squared equals 0 defines a curve with an isolated point, and that's such a singular point. But in addition to those 10 blue singular points that come from the projection, there are 36 red points that come from just by projecting, right? If you have a curve in 3 space that you get by intersecting a cubic surface and a quartic surface, and you project into the plane by the degree genus formula that we often ask our students in the qualifying exam in the math department, there will be 36 red singular points in the plane. So the upshot is there are serious obstructions. So even if you see this nice convex body in the plane that looks, not too bad, right? It has a very, very high degree of singularity in the complex curve in order to be liftable into 3 space. So here's the questions I like to address in the remaining 10 minutes maybe. I will not go over time too long. So let's look at a generic spectrahedral shadow of type NDP. N is the size of the matrix. D for downstairs is the downstairs dimension. And P for projection is the codimension of the map. So here's an example. Okay, so this convex hull of this red curve, that's an example of a spectrahedral shadow in the plane that we will analyze in a moment. So the 3 questions I like to address and answer is, what ranks do you see in the boundary? So the upstairs matrices, they have some rank. These are going to be n by n matrices of some rank. And then what are the possible ranks that you see in the boundary? How many irreducible components are there in the boundary hypersurface, and what are the degrees of those hypersurfaces? Those are the questions I would like to answer. Okay, so let's take this example. So here's a spectrahedral shadow of type 3, 2, 2. So 3 is the size of the matrix. There are 2 x variables. and there are two y variables that I eliminate. Okay? So this formula describes a four-dimensional spectrahedron of degree 3. I'm projecting it into the plane, and I get this shaded picture. And the algebraic boundary consists of two curves of degree 4. There's one curve, that's the red curve, this cardioid curve, and that's given by this polynomial. And the preimages upstairs, the general preimages, will have rank 1. So the rank 1 part of the exposed boundary upstairs gets mapped to the red part of the boundary. Okay? That's an irreducible curve of degree 4. There's also 4 lines in the plane that form an irreducible curve over Q. Okay? And that's the other part. So if you look at the rank 2 locus, so if you take the 3 by 3 determinant and you project it down, it ramifies along 4 lines, and those are the 4 lines that you see. And in this particular choice, only 3 contribute to the actual boundary of the spectrahedral shadow. Okay. So I'd like to ask the question, what happens in general? So this is an example. This is the behavior that you see for p equals 2, d equals 2, and n equals 3. What can we say about these polynomials in general? Well, here's the answer. So there's something called the algebraic degree of semi-definite programming that was studied together with Nie and Ranestad, and then further developed, and an exact formula was given by von Boltzmann and Ranestad. And I'm not going to define that, but I'm going to sort of define it implicitly. So let S be a generic spectrahedral shadow of this type, NDP. And the theorem says that the rank of a general point in the boundary will be in some range. There will be an upper bound in terms of n and p, and a lower bound in terms of n and p, independent of d. That's sometimes called the Pataki range. Now, if you look at all the points of rank R, they form an irreducible component in the algebraic boundary of our shadow. And that algebraic boundary is an irreducible hypersurface whose degree is independent of d, and it's equal to this number, delta of p plus 1 n comma r. Okay? Now, if d is 1, take a breath. Okay? If d is 1, so if we have this high-dimensional spectrahedron, we're projecting it onto the line. That's semi-definite programming. Right? So projection onto the line, the 2 endpoints, right? That's maximize and minimize. So for d equals 1, and that's the definition of algebraic degree of semi-definite programming. So sort of the new part of this theorem is that this is independent of d. And rather than even attempting to give you a formula, I'm going to give you a table. And in color, you have the 2 examples we saw so far. Okay. N, the columns, is the size of the matrix. So this is the column for 8 by 8 matrices. The rows, 3, 4, 5, that's P. That's the codimension of the projection. R is the rank that you see in the Pataki range. So for example, here, way at the bottom, there are 4 possible ranks. So what we're saying is, if you take a 10 by 10 matrix, you specify a spectrahedron upstairs, and you map it down the codimension 9 projection, then in the boundary, you're going to expect to see matrices of degree 9, 8, 7, and 6. And these are the degrees of the polynomials that cut out those red boundaries.
Again, Bernd?
Yes.
So when you do p equals n minus 1, that's semi-definite programming?
If you do d equals 1, so if we're projecting, so if the shadow is just a line segment.
I see, this is independent of d.
Exactly, it's independent of d. So the punchline is, yeah, so it's independent of d. So these are the 2 examples we saw. So for example, if p is 1, n is 4, and the rank is 3, that was our curve with 46 singular points in the plane. And then this was the cardioid example that was p equals 2 and n equals 3. Okay. Almost done, right? So Only 3 slides. So here's an example. So I'd like to end by talking a little bit about the degeneration aspect. So let's do an example with 4, 2, 1. Again, n is 4. That means we have a 4 by 4 matrix. And then d is 2. So the shadow is in the plane. And p is 1. There's 1 y coordinate. So this is a projection from 3 space into the plane. Now that's exactly our curve of degree 12. Okay, so let me pick epsilon to be 0.02. Okay. Well then, you know, I get this degree 12 curve. Here it is in purple. It has 46 singular points over the complex number. And you can see the spectrahedral shadow. Okay. Now what we're really interested in, what Stephanie really is interested in, what's happening as epsilon goes to 0, right? Because if epsilon goes to 0, then we have some structured example that we really care about. Okay? So what happens as epsilon goes to 0? Well, this curve of degree 12 becomes a degenerate curve of degree 12 consisting of 6 double lines. Namely, the 6 lines spanned by the 4 vertices of a regular square. This is a representation, this is a lifted, extended representation of the regular square. Okay? There it is. Now what are these 2 red lines doing? Well, they appear algebraically, but they appear to each of these lines has multiplicity 2. So as they take the epsilon and make it positive, they sort of disappear. Right? Like a double root can disappear. So it disappears. Okay? So this is, I think, what's important to understand. So the second to last slide is titled Pablo. So students from MIT, Hamza and James, have a wonderful new paper where they succeed in representing the k-gon, the regular k-gon for various values of k. And this is an example we took from them. So this is the representation of the regular hexagon. Extended formulation for the regular hexagon. So this is our shadow. So here n is 4, d is 2, p is 3. So this is a 5-dimensional spectrahedron. And then this 5-dimensional spectrahedron represents the regular hexagon. Now algebraically what's going on? Well, you look in the table. All right, so p is 3, n is 4. So there are 2 possible ranks. So the rank can be 3 or 2. On rank 3, we're expecting an irreducible curve of degree 8. On rank 2, we're expecting an irreducible curve of degree 30. Right? And we can see a shadow of that complexity in this diagram. So if we take the 6 vertices and we draw all the lines, we actually see a curve of degree 30. So let me try this. So 6 choose 2. Is that 15? Okay, now I forgot. Got ahead of myself. So anyway, so there is an irreducible curve of degree 30 that degenerates to this. So I think what's happening, we have the 12. So I think there's 15. Exactly. So there's 15, and it's actually each has multiplicity 2. So it's this curve, you know, degenerates to this picture. So with minus 3 minutes left, let me end. So the conclusion of the second paper is that we do now understand the generic case. So if we have random matrices AI, Bj, and C, we understand exactly the polynomials downstairs in x1 up to xd that describe the boundaries of a spectrahedral shadow. Be very, very interesting, of course. Now lots of work is needed to look at specific situations. So if these matrices AI, Bj, and C are not generic, but maybe they represent a particular hierarchy, or they represent a particular family of combinatorial optimization problems, how does this generic situation specialize as epsilon goes to 0? Thanks for your attention.
So, I assume in this table you don't list possible degenerate cases in case, as in you have a set of matrices, but But their combinatorial type is only achieved with measure 0.
That's correct. This is what happens with probability 1. So if you pick up matrices A, I, B, J, and C randomly, and then with probability 1, this is what you will observe.
But for your previous paper, you understood all the possible scenarios.
In this case, yeah, exactly. It's a very, very tiny case. For 4x4 matrices in dimension 3, there we understand everything that happens. So that's the first. So here, that's the first case where we can actually describe, quote unquote, the combinatorial types of spectrahedra. So there we understand all types. But still, the degenerations are still interesting. So I should maybe say there's still interest. For example, this one is not generic, right? So this is not generic in the sense there's an entire curve worth of singular points. So that we haven't worked out yet, but in principle, we could do it in that case.
Can you say something, in your table, are there ways of computing those, like asymptotics of those numbers with integral geometry or something?
Yes. So there is a formula.
Well, the formula is...
There's a formula. So yes, so you could study the asymptotics.
Somehow is there supposed to be like a geometric, an integral meaning or...
Yes, so these are certain intersection numbers. So there's a technique called Schubert calculus that gives these numbers. Perhaps more interesting, there's another question you can ask that's perhaps even more interesting, and again, Peter and the former student have made a contribution. You can ask, what's the probability that these cases will be attained? Right? So we're saying, if you pick a random, 10 by 10 matrix, in this many dimensions, every optimal matrix will have rank 9, 8, 7, or 6. And there's an integral that you can try to evaluate that tells you what the probability distribution is on that case. And that's very, very interesting. So there's an integral geometry formula that gives you information.
Is it clear that what we computed is the same as you did? Something that's not? I think so. Is it? You should talk about that.
So this thing went again and it goes.